Hello and welcome to another power electronics class. Uh, we didn't have any class on Monday, obviously, because of the Labor Day. And last week we spoke about, we finished at some introduction about EVs and the applications of power electronics on EVs. And some applications of power electronics and grids as well, like like HVDC, high voltage DC. This week we will continue and we will mention some applications of power electronics, especially in smart grids and microgrids. And then we will continue with some concepts of conversion and rectification and inverters. So this is an example of an ELAN node. These are the future grid system nodes. And these systems are built entirely sometimes with power electronics. These usually have an intelligent power rotor that sits between the meter and the breaker box. They usually contain an IoT. Do you know what IoT stands for? Internet of Things. Okay, so anything from your fridge, your Ring doorbell camera, everything that is connected to internet, right? Like most of these home appliances, Alexa, if you have an Alexa or a Google Home or a smart light, these are they usually have a uh, microcontroller that is connected to the internet. Most of them are based on the ESP32 or they call it Node MCU. And you can remotely control the device, or you can gather data and information from that device. And these IoT devices, um, they are used for weather and time of use pricing data. And they could determine what time of the day the usage went up or down. So it would give us real-time data monitoring of a solar system, for example, or a load, for example, a house. These direct power from grid or local assets such as solar storage and generators. They operates in island or grid connected mode. And one example that we give is what we call grid tied or off-grid systems. A grid tied system could be a home that has solar panels on the roof and it has a two-way meter during the night that we don't have any solar power. It buys power from the grid, and during the day when it has excess energy, it can sell back energy to the grid. And we have the model predictive security systems as well. This example here, you have a solar panel, battery pack, the control system, two-way connectivity to the grid, and a backup. Usually it could be a generator, gas generator. Most of the time you don't need this if you have a good battery storage system. This is an example of electricity faces the challenges that I mentioned. One major challenge that we have right now is cybersecurity for these smart grids, um, and also managing the power in the grid. I don't know if you're familiar with this curve. This is called the duck curve. And what this shows is the power consumption and power production in a solar system. So during morning hours, usually the power usage is low. And then when everyone wakes up, you have a small peak around like 8 a.m. Everyone is waking up, turning on their toasters, and then everyone goes to work or to school. That power consumption dips, and then in the early afternoon, evening. Again, everyone is back, turning on the lights, washer, dryers, everything, it goes up. So this is actually the power consumption usually in a grid. And the problem with this is that solar power generation looks like this. You don't have any solar power, and then you have a peak, and in the afternoon, it goes down. So this is what we generate using PV panels or photovoltaic or solar. The red is our load consumption. So there's a big imbalance between these two. Okay. How can we fix this? Store the energy, perfect. And storing energy, we have multiple ways, but the easiest way to do it right now is to use battery storage, which currently are expensive. So a big hurdle to PV and solar panel. Right now, building a solar power plant has become cheaper than building a coal power plant. But the problem that we have with solar is that we don't have the power when we need it. So in addition to the solar, we have to build these big storage, battery storage systems, which are currently, the price is coming down for a lithium-ion battery, obviously, but they're so expensive. There are other forms of solar energy storage systems as well. One type of system that has become very popular recently is to store it as a in these what we call the sand batteries. So sand batteries, generally, what they do is they imagine you have a big tank, you fill it with sand, and you put these heat elements in them. And what you do is when you have solar power, you heat up the sand, and during the night, you run a water pipe through it, you pump water, generate steam, run a turbine, and that could store, sometimes could store, if it's a very large unit, it could store power for 2-3 days. And it's cheaper than another type of storage system is hydro storage. So you have 2 tanks, you pump water to the upper level tank, and then you leave it and you generate power. Both of these require a lot of land, and they have moving parts. So you have to maintain the generator, the pump. But for a battery system, the good thing is it's small. You can put it in the basement of a house, doesn't make any noise, doesn't have any moving parts. But it's more expensive than that. But the technology is growing exponentially. Now we have solar power, photovoltaic panels, we have wind, LEDs, batteries, IT, storage system, and so on. But the disruptive impacts are the operations, revenue, regulatory planning, resiliency of these systems. As mentioned, the reliability is a big issue with renewable energy. The wind doesn't blow when we want it. The sun doesn't shine sometimes when we want it, especially during the night. So we have to address these systems. So when we automate all these systems, and especially with the renewable energy, we build a grid that we call the smart grid. And the smart grid is technically this grid that all the components of the grid, the transmission, the load, the generation, all of them are controlled with a smart system. Nowadays, AI has become very advanced, and in some parts, you can actually incentivize the customer to give you control over their appliances. And they are doing that in some parts of California. What you do is you would put these smart plugs in your home, for example, and the power company would have control on some parts, like for example, on your HVAC. So they'll actually provide you with a smart thermostat like Ecobee or a Google Nest, and they would have control on the thermostat. So what they would do during peak hours, like during the early evenings, they could reduce or increase the temperature of your home, so they could balance the system, the grid. So instead of, firing up another gas generator, what they would do, they would reduce the consumption by having control over. Imagine you have control over 10,000 HVAC systems, and you just reduce them by 10%, then you don't need to run a 5 megawatt, for example, gas generator, and you can control the peak. The final goal here is to flatten this, to make this as flat as possible. Let me draw it with a different color. So we like this to look something like the green line that you would see. We don't want to have sudden peaks, because it's going to put pressure on your generation, or generators, on your transmission, and so on. So this is one way that they do it. Another way that they would do it is what we call the EV to grid. So nowadays, most EVs, they support a EV, they are a two-way system, meaning you could connect that to your home, and if there is a power outage, you can use your EV as a backup system. And since that has a huge battery, 50 to 100, sometimes 120 kilowatt hour, that technically could run your home for a couple of days without being connected to the grid. Now imagine that battery package is connected to your wall connector, and the power grid company has control over when to get power and when to charge it. So what they would do is, usually after midnight, they would charge the car, and during the peak hours, they would discharge it. And they pay a very good rate as well. Usually when you charge at midnight, or the power price, the kilowatt hour power price, is, you can have a fluctuating plan, meaning during midnight it's going to be 5 cents per kilowatt hour, 7 cents. I think it's an Amarillo Excel is doing 7 cents right now, and during the peak hours is like 14 cents. So what you can do, you can charge your car at midnight and then sell back to the grid. So you're going to make money out of your car without even moving the car. And sometimes you can make a lot of money out of these systems if you just, a lot of I see new investors are working on building this huge power storage systems, battery storage systems, and they just put it somewhere near a grid, connect it to the grid. They will charge the battery and buy the power from the power company at like the lower rate, and then they will sell it back. And it's just sitting there, and what it's doing is just balancing the system. And as I mentioned, we want this curve to be as flat as possible. So all of these require a lot of power electronics. You need to be able to, control the flow of power in real time, the frequency, the voltage, the current, everything. So the grids currently have become a cyber physical system. We have different components, as I mentioned, the network, the consumers, the generators, and all of that. And this is a graph that shows the grid. We have the cyberspace, we have the actuation information, we have the real space, object domain, and physical sensing. If you have, you may have smart grids with me next semester, we would go deeper into details on those smart grids. This is an example of energy system integration, or ESI. This is a process of optimizing energy system across multiple pathways and scales. It's for building clean, affordable, reliable energy systems. You can see this is some projection of what today's systems look like. We have island villages. This picture is from 2019 or 18, I think 2018. So we obviously have 10 megawatt system, the campus, 100 megawatts, which are the communities, and 1 gigawatt systems, we have 100 megawatt systems easily. We can do that with solar panel right now. Some interesting statics and information about the renewable energy system, why we need it, because of, as mentioned, geopolitical and security reasons, and the financial benefits, environmental benefits of renewable energy. Obviously, CO2 and green gas emissions is a concern that we won't have when we have a smart grid, a renewable energy system grid. But the problem again is the control, having the control over the smart grid, which requires a lot of power electronics. This is the US electric grid today. Obviously, these numbers change. These are higher. This is, I think, from 2022, 2023. It was 850 gigawatt base load, 1,250 gigawatts summer peak, because obviously summer, when the weather gets warmer, everyone runs the HVAC and power increases. 7,000 operational power plants, 3,200 utilities, 60,000 substations, 642,000 miles of high voltage transmission lines, 6.2 million miles of distribution circuits, and 59 million customers. So imagine this system should double by 2030. Some estimates say 2030. The power generation side, because of the rise in AI. So one cloud AI, system, one data center that Meta built consumes more power than a city the size of Amarillo. So huge power demand. That's the reason they are going, and they're actually opening up some nuclear power plants again, like the 3 Mile Island nuclear power plant, because of the huge power demand. They see that if each time you search on ChatGPT, it's almost amounts the same power of boiling up a cup of coffee. So a lot of power consumption.
With that, are you thinking how much computing the system has to do?
I have to give you the exact information, but it's a lot of. There was a famous tweet by Sam Altman a few months ago that some people are used to say thank you to ChatGPT, and ChatGPT replies with "You're welcome" or something, and that costs them millions of dollars per year just for that word, and you can search for that tweet, that just one word and like replying, because these are, I don't know how familiar you are with AI systems. They measure the processing with teraflops, and it's so for a normal computer, you would have a normal GPU with few gigaflops, and a AI data center have few 100,000 GPUs, and they work in teraflop. So it's like, imagine your GPU, which you're playing like the latest games on, multiply that by 10, and then multiply it by 100,000, something like that. So 1,000,000 times of a normal computer, like a gaming computer or something like that. But I'll give you the exact numbers. It's changing. They're now working on SLM. Have you heard of SLMs? So SLMs are, we have LLMs, which are ChatGPT large language models that need these huge computational power to run a normal chatbot. And now they're working on SLMs, which are small language models, which are good for, replying to simple texts and writing emails, drafts, something like that. And they're trying to minimize the power consumption and the model so it could be implemented inside a smartphone. So I think in the next like 5-10 years, the main focus would be to reduce the power, come up with better, uh, models that could run on your phone, so you don't need to be connected to internet all the time, and it could automatically, reply to your emails, reply to your chats, give you, basic information if you need, and do some image processing without, requiring connecting to the cloud.
It's similar to what Apple is kind of doing with their message summary.
Yes, exactly. Yes. I think that still requires connection. Obviously Apple, I think it's like 3-4 years behind an AI race. It's not big, yeah. Uh, and but yeah, they're working on a new system, especially Apple, that they could be implemented. And it's going to give huge advantages. Imagine you're in a rural area or you're going on a trip. You don't always have access to internet. So it's going to be very, very beneficial. And the good thing, you can imagine you have a small model that you can put on a camera without requiring connecting to internet, and it could process, pictures, images in real time. It could read text in real time. So it's going to be very future. It's both exciting and I would say a little bit I'm intimidated. The reason is I see this a few years ago, especially in computer science. I'm sorry for going a little bit off topic, but a few years ago, um, I saw a lot of students interested in computer science, and most of our students would find a job immediately after graduation. Now I see that a lot of these computer science, especially the entry level coding jobs, are completely gone, just gone in 2 years. So imagine what happens in 10 years. So there's not a lot of interest in computer science. You would see that a lot of them are changing majors. Not a lot of jobs for computer science. I have a friend that works at Microsoft, and he told me he runs a team. He used to run a team of 15, and now it's down to him and 3 more guys. So the thing is, previously for example, if you wanted to build a smartphone app, you needed a back-end developer, a front-end developer, UI, and so on. You needed like a team of 5 at least. Now, one person could do job of 5. Just the AI has become so powerful. I don't know if I've used it for coding. It's amazing at coding, very good. So if you use it and I would highly recommend that you learn how to give it prompts and learn how to do coding.
Because those jobs are now replaced by people that know how to write prompts and stuff.
Yeah, exactly. And again, now because the efficiency has become, so high that one person can do the job of 4 or 5. But you need to still know the principles of how to code it. If you don't know how to run let's say, a Raspberry Pi, even if you know how, like the coding part, you can do it easily. Now, electrical engineer could do all the jobs that require, someone that knew coding. You can do everything by yourself, but you still need to know how the system works, the concepts behind it, but you're going to be much more efficient. And so I would say a lot of editing, basic level coding jobs, all of that would be eliminated. Now there are a couple, websites that you just give them prompts and builds you. I don't know if you use some of them. It will build you a smartphone app in a few minutes from just simple prompts. You can build a iOS app. Okay, so some information. This is the grid transformation and the projection until year 2050. You can see the rise of solar power and wind power energy, and the solar is with yellow, and you can see the wind with green. and the blue is going to be oil and gas. Actually, Texas is leading in wind energy and one of the leading states in solar as well. Huge potential in Texas. And you can see now there was a turning point around 2022, 2021, 2022 that wind and solar became cheaper than new coal power plants, and now they're just taking over. The good thing about solar wind, it doesn't require any fuel. So any changes in fuel price like gas and oil doesn't have any effects on it. So when you build it today, you exactly can predict how much it's gonna produce for the next 20, 30 years. But for a gas power plant or a coal power plant, you don't know, maybe next day the price of gas would, increase or decrease. And it's same thing for coal and oil as well. Some problems are with the grid infrastructure, which are aging. The accelerating of retirements of coal-fired power plants, increasing new generation and renewable generation systems, coal-fired unit retirements driven by low next generation of new generation power plants like solar and wind, as I mentioned. And the EV growth continues as well. That puts a little bit of challenge and pressure on the system and the rise of AI systems as well. So today's and older generation grids were large power plants, top-down power flow models, and synchronous machine dominated. Future grids would be small distributed generations, modular microgrid architecture, and inverter dominated, which the inverter dominated is the opportunity for innovation and requires a lot of power electronics. Now, the role of power electronics and future grid and future systems. Traditionally, we had two types of power conversion systems. We had linear electronics transistors in active mode, like in their linear region, like transistors, which acts as a variable resistor for control. The problem is that their maximum efficiency is 50%, and that's even uncommon. So around 50% of the power would be wasted. They have low conversion range. They have greater V drain and smaller efficiency. And they are only good for low power applications. You can't use them in high power because the efficiency is so low that it's gonna 50% of the power. What happens to the 50% that it's not transferred? Imagine I have a DC to AC and I'm using a transistor and only 50% is transferred from DC to AC. And then imagine I have a 10 kilowatt. 10 kilowatt is very high for this system. Imagine I have 100 watts and only 50 watts goes to the AC. What happens to the other 50 watts? It generates heat. Okay, now imagine I have something that is 10 kilowatts. A 1 kilowatt could easily melt the transistor. So you can't build a high power system. It should be around maybe few hundred watts maximum. So for higher power, like 50, 40 years ago, if they wanted to convert DC to AC, so imagine they had a DC power source and they wanted to convert it to AC. So DC to AC. What would they do is they would use a DC motor and they would couple it to an AC generator. And they will run the DC motor, and the DC motor, which was connected to the AC generator, would turn and generate AC power. So for high power, let's say 1 or kilowatts above, like 10 kilowatts, 100 kilowatt or something like that, what they would do actually to convert AC to DC or DC to AC, and you can do it both ways. You can have an AC motor, DC generator, you can have a DC motor, AC generator, you can have an AC motor, AC generator, and a DC motor and a DC generator, okay? And you can convert these two. But some problems that this have, first of all, if you want to imagine you have an AC to DC system, obviously you can't put an AC DC generator in your home. It's going to create a lot of noise. So very large systems, now you can build it in a space that is the size of your fist, the same system, instead of having too large a motor and a generator. These systems can still be found and used. The problem they have is they are maintenance intensive. So everything that has running parts, you need to change the bearings, you need to change the oil if the bearings need oil, and you're gonna have wear and tear on the system as well. Maximum efficiency is around maybe 70-80%, and we have poor load regulation as well. What does this mean? If you have a generator that is connected to a load, imagine you have a heater on the other side, and you suddenly turn on the heater, you have a switch, you turn it on. When you have load on the generator, what happens when you suddenly switch the generator? It's gonna put pressure on the generator, and it's gonna immediately reduce the torque because it should work harder to generate the power. So what happens is the RPM drops, and for that to compensate, and you need to have a constant power delivery, then you need to increase the generation side power. So that creates a lot of problems. So you want to regulate it for a power electronic system. I would explain later on. Simple feedback will solve this problem. But if you have a motor generator or a mechanical system, it's going to create problems. This is simplified. So the older generations, low efficiency, a lot of maintenance. We don't use them again. And I'll explain what we use right now. And this has the reason that EVs and renewable energies have actually improved significantly in the past years is because of the improvement in power electronics. So this is simplified block diagram of power electronic system. We have the electrical input source, we have power electronics, we have the load, and we have a feedback system. And if you want to go more into details, this is going to be a detailed system of a power electronic system. We have input, which is a form of electrical energy, which could be AC or DC power. We have filters and rectifiers. If we have a DC, we want to get rid of the noise most of the time. We have, and here you can see it's mostly unregulated DC voltage. So if it's a DC that looks like this, or looks like this, has a little ripple, we wanted to make it clean like a flat DC signal. Then we give it to a power processing stage, which is a power electronic circuit. Then we have host stage, which is another filter. We have the load, and then we have a feedback, and the load could be electrical or mechanical load. And then we have electrical variable feedback and mechanical variable feedback. And then we have the control circuit. We have the switch drive, which again controls the power electronic circuit. And the switch drives are the interface between control and power circuits. This is an example of, can you say tell me what type of power conversion is this? So on the left, we have the input. On the right, we have the output. So this is an AC to DC system. This is a typical AC to DC system. And we have two different systems, actually. We have unidirectional systems and bidirectional systems. So this is a one-way system. It's just from input to output. So conversion type descriptions, we have different conversion types for power electronic systems. The PE systems perform one or more of the following conversion functions. We have rectification, which is AC to DC. We have inversion, which is inverters, that's DC to AC. We have cycloconversions, which is AC to AC with different frequencies, or we have AC to AC with same frequency, or but sometimes they could have different shapes of signals. So you may have a triangle signal or a square signal, but what you want in the output is a sinusoid. This is used a lot, especially in pure sine wave, what we call pure sine wave HVAC systems or inverters. And what they do is you have a DC, and it's very easy to use an inverter to convert DC to AC. The only thing that we need to convert a DC to a simple AC is to have a switch. So if I have a switch and I turn on and off the switch, I'm going to have a pulsating DC or an AC. This AC signal is called a square AC signal. And the problem that these square AC signals have is, if for normal use, if you wanted to use it any electronic device which has it's charging a battery, or it's going to be no problem for that. But any AC motor that is connected to this, because it's suddenly moving from positive to negative and you don't have a smooth transmission, it's going to put, and I'll explain this later, we have different harmonics, like this first, third, and fifth harmonic, and that's going to create, I would say it this way, extra pressure on the motor. It's going to heat up the motor, and it's going to be bad for the motor. You would hear that knocking sound. So for those type of AC motors, having a pure sine wave is very important, because a square sine wave, square AC signal is going to damage the motor. Therefore, we use a cycloconversion, for example, to convert this pulsating DC or this square signal to a perfect sinusoid signal. And then we have the conversion from DC to DC, usually when we want to convert one level of DC voltage to another, which is called a buck or boost. Buck reduces the voltage, boosts the voltage. So if I want to go from 12 volts to 5 volts, or from 5 volts to 12 volts, okay? We don't have, so in AC, we can easily regulate the voltage and current by using a transformer, okay? What happens if I give, so imagine that I have a transformer, okay? We have the primary winding, we have the secondary winding. You already know that for a transformer, V1 to V2 is equal to N1 to N2, the turn ratio. And this was actually a FE question as well. So what if I give 12 volts transformer, and the primary winding is 100 and the secondary winding is 10? What would V2 be? Whoever solves this actually gets an extra point on their next homework and the first homework. So I have a transformer. The transformer's connected to a battery of 12 volts. N1 is 100, N2 is 10. What is V2 or output voltage in this system? I think this was a FE question for 2019. I have to double check. What is it? So V1 over V2 is N1 over N2. V1 is 12. V2 is unknown. N1 is 100. N2 is 10. Yes? So V2 is equal to 10 times 12 over 100. Am I correct? Yes. So it's going to be 1.2 volt. Did you get 1.2 volt? Yes. All of you? Okay. That's completely wrong. Why? Because we don't have such a thing as a DC transformer. A transformer only works on an AC signal. Okay. So if you give it a 12 volt, you're going to have 0 volts out there. We don't have such a thing as a DC transformer. This was a trick question from FE. Okay. Transformer only works on an AC signal. So what would you do if you want to boost, you want to decrease or increase a step up and a step down DC? What you technically would do is you would convert it to AC, boost it, and then convert it back to DC. Now I'll show you how we do that. Technically, what is done is using a switch system. So keep in mind that a transformer, we don't have such a thing as a DC transformer. The transformer does not work on a DC signal, okay? I don't want to go back into the physics and electromagnetics. That's a topic for a different course, but just for now, remember this. So the power flow could be unidirectional, input to input, output, like, or it could be bidirectional. It could be the load side could be the input or it could be the output, both. This is an example of a non-isolated DC to DC converter in the continuous conduction mode, or CCM. Before I start this, I want to give you some perspectives of how these systems actually work. Okay. So we learned that we cannot use a transformer to convert or to amplify DC. Okay. Then how can we amplify a DC signal? How can we regulate a DC signal? A DC voltage? And I'll give you a practical example. You all had an RC, maybe car or a plane when you were a kid. Do you know how they work? How does the RC transmission and receiver side work? Have any idea? So the RC car has a motor, yes? And that motor is a DC motor. And you can control the throttle or the RPM, the power of the motor. In a DC motor, how do you control the round per minute? The speed of the motor. How do you control it? By controlling its voltage. Yes. So for an AC motor, you have to control its frequency. For a synchronous motor, for DC, increasing the voltage increases the speed. Decreasing the voltage decreases the speed. Okay. So for a DC motor, and you can, I think you had maybe experience with controlling a DC motor by simply changing the voltage. So how could I change the motor on an RC car? So imagine the DC motor is connected. One way to do that is to use a variable resistor. Yes. To do that, you have to be physically on the motor and have a variable resistor, change it and adjust that. It's not practical, first of all. Second, it's gonna waste about 50% or more of the power. So this is out of the picture. Another method that we use is called PWM. PWM is pulse width modulation, okay? So what we do is we have a square signal, and how do we build the square signal? We have a DC signal, and that is connected to a switch, and I have a control system connected to the switch, and this is going to be my load, and I would connect and disconnect the switch. So while I have a DC in the input, and I would have a pulsating DC or a square signal in the output. Okay. So pulse width. So again, pulse width modulation. In pulse width modulation, I can control the width of this pulse. Okay. Now you may ask, the width of the pulse, what does that do for us? How could that help? If I have a pulse like this and 50% is positive, 50% is 0, and imagine the maximum voltage is 10 volts. So I have 50% of the time the switch is on, 50% of the time the switch is off. Okay. If I want to get the average of this signal, what would the average of this signal be? How much voltage do I see in the average? 5 volts, perfect. So average of this would be 5 volts. The maximum voltage is 10 volts. So if I take an average, it's going to be 5 volts. Okay. How do I take an average from a pulsating DC signal? How can I take an average from the signal? What type of, what elements can I use to average this signal? I need something to store energy. Okay. What elements store energy in them? I'm sorry? Battery, perfect, great. The only problem with battery is that it takes time to charge and discharge. I need something to quickly charge and discharge. Yes, I can use a capacitor, inductor, and what a capacitor does, it charges and then it discharges. So you're gonna have something like this, charge and discharge, and if you have large enough capacitor, same thing that you had in a rectifier. Do you remember what you had in a rectifier in electronics? Yes? You would connect it to a capacitor. So you can use a capacitor to take the average of this, okay? So now, if I have control of the speed of switching and I close it 100% of the time, if I close it 100% of the time, what would my average voltage be? 10 volts, yes? What if I close it 100% of the time? I'm sorry, 100% of open. I'm gonna have 0 volts, yes? What if the system is turned on 80% and off 20% of the time? Let me erase. Can I erase this? Did you write this down? I'm gonna draw it on the top. So imagine I have control of the switch, and now I've turned it on 80% and turned on off at 20%. So it's 80% on, 20% off. 80% on, 20% off. Now, the average would be around here. Am I correct? Yes. It will be around 80% of the full 100%. If this is 10 volts, the average would be around 8 volts. Okay. So it's going to look, the average is going to be somewhere around here. something like this actually. So simply by changing the switching speed, I can have a control over the output voltage. So what this does is technically this, imagine this is connected to a battery on the motor. And the only thing that I have control over, it's a capacitor and this is connected to the negative. I have control over the speed which this switch is closing and opening. If it's completely closed, the motor is at 100% and it's running full speed. If it's completely open, it's 0. If it's open and closed at 50%, so imagine it's open for half a second and closed for half a second, then you would run at 5 volts. Obviously, the frequency is much higher than that, around like a few kilohertz. But if I do 50%, I would have 50% of the voltage, 50% of the power, and so on. Is it clear? So imagine if it's off 90% and then it's on just 10% of the time. Then where would the average be? The average would be down here, around 10%. So this is 90%, 10%. So I would have around 1 volts. Okay. So this is a much more efficient way, and this is actually how all these RC systems work, using a pulse width modulation. So again, pulse. Sorry, my pen doesn't work well. So we call it pulse width modulation. Is it clear? Yes? Okay. And we could scale up this to even hundreds of volts. It also works. And this is the principle of an inverter as well. So you can see here, we have our switch. This is our switch that I mentioned before. And we have the storage unit, which is an LC. So the switch, you can see that the voltage is going from positive, negative, and I could connect this to the ground as well, or just connect it to the negative. So in this case, it's going from positive to negative. In our previous one, it was just disconnecting it. So it was going from positive to 0. But you can obviously go from positive to negative as well. So the principle of steady state converts analysis definition of steady state inductor the volt-second balance, capacitor charge balance, small ripple approximation, average values and steady state, use of power conversion principle and converter analysis, and the application of analysis techniques to classic converter topologies, buck boost and buck boost. And I'll explain what a buck is, what a boost is, and what is buck boost is. So what we will learn is the principle of the converter analysis and how we do that. And on the second one, you can actually see the ILT and the output current, which is actually, this is the average output current that we get. So I don't think we have enough time to go through this, but for the next few weeks, what we would have, the course content would be non-isolated DC to DC converters, discontinuous conduction mode or DCM. We would go through the descriptions of DCM, at what operation condition does DCM occur, application of steady state analysis principles to converters in DCM, the buck boost, and what we call them CUK or converters. And we have properties of converters in DCM. And these are some examples of DC to DC converters. Now, this, as I mentioned, is an example of a classic inverter. And as I mentioned, pulse width modulation can be used both in DC to DC, as I mentioned, and also DC to AC as well. So one example of a DC to AC is, for example, if I have a DC in the input and I can connect that simply to a switch, and I can have a load, and I can have control over this switch. And by simply turning on and off this switch, I can create a basic AC signal. So now if I want to have a pure sine wave, or if I want to have a triangle base, I can simply add a capacitor here. And what it does is the capacitor is charging and then it's discharging. Actually not smooth as a sinusoid, but it's charging and discharging. So in the output, you're going to have something that looks like this. Better than a pulsating DC square, it's a triangle, but you're going to have a little bit smoother. But if you want to have a pure sine wave, one way to have it is to have a very high frequency system that rapidly goes from positive to negative, from positive to negative, from positive to negative. And what we do here is by averaging this. So if I average these two first ones, the voltage would be around here. If I average the two second ones, it's going to be it. So I'm creating a step type of signal. So you're going to have something like this. Okay. And I'm just going to put it in with, and when you connect them together with a capacitor or anything, you're going to have something that looks very, very similar to an AC signal, a sinusoid signal. And this is exactly what we have here. So this example, it's 90% negative, for example, 10% positive. And then the average would be around here, you know? And then for the next one, it's going to be a little bit less negative, a little bit negative. And then you can see that we can create something that is very close to sinusoid. But the problem here is that you need a very advanced switching system. Normal switching, you can't do it like multiple thousand times per second. So this is in the range of kilohertz, megahertz, sometimes even gigahertz. You need to have a very fast switching system, very good filter. That's the reason pure sine wave inverters, if you search in Amazon, they're usually 4 or 5 times the price of a normal DC to AC inverter, because a normal DC to AC inverter is just a square, AC. If those cost for 1,000 watt, they are usually $30-$40. The pure sine wave, very good ones, are above $500-$600, so sometimes 10 times the price. And they're much bigger, like 5-6 times the size, because they require a lot of filtering, sophisticated control system, and so on. So we can create AC signal from DC using switching, okay? And depending on how sophisticated our switching system is, we can have a very good DC to DC or a very good DC to AC. Now, what if I want to go from AC? Imagine I have this and I want to go to a DC like this. What do I do next? What can I do to convert AC to DC? What type of circuit do we need? Rectifier, yes. I can simply use a bridge rectifier. So creating a rectifier, because I don't need any switches, okay? I don't need any switch. I don't have any control. So I don't need any microcontrollers. I don't need to program anything. It's going to be much easier. So DC to AC inverter, expensive, $400, $500. But AC to DC, you just need a bridge rectifier with a few capacitors, $2 max, high voltage. So AC to DC, very cheap, very easy, doesn't require any sophisticated parts, elements. But DC to AC, fast switching. And Fast switching requires transistors, the IGBT transistors, which are very, very expensive. Very, very complicated. Okay, thank you so much. That's it for today. I will see you next week, and I'll explain more about the switching concepts.